There's actually, you'll see that in the definitions that we need, even though characteristic classes is an application of cohomology, and I'm developing an approach to cohomology, the level of generality we need will be with using some vector bundles. So convenient that we've been talking about vector bundles. And there's one more notion. So definition, I'll assume you know what an orientation is. It's just a equivalence class of bases, ones which are related by linear transformations of positive determinant, right? So any vector space has two orientations, and an orientation of a vector bundle is just a consistent choice of orientation for each fiber, and it's so as a choice. What can we mean by consistent? A few things, but is a choice of orientation. Consistent with the trivializations. With all, say, choices of trivializations. And in particular, what that means then is those transition maps must be of positive determinant. So the transition isomorphisms, I think I was calling them phi ij, are positive determinant. In a more group theoretic approach to the subject, and which we will discuss at some point, I mean, just like the choice of metric let us go from the general linear group to the orthogonal group for these transition functions. This is a much less drastic reduction in some ways, although it's not, unlike that which is sort of homotopically trivial, because GLN and ON are homotopy equivalent, Graham-Schmidt being a way to get an inverse to the identity. This one actually is a choice of two components, so it's not one of two components, so it's not a homotopy equivalence when you go from all invertible matrices to positive determinant ones, of course. So let me give you a little exercise on that. Kind of a standard thing. Excuse to learn a little bit of multilinear algebra. So an orientation is a section, is equivalent to giving a section of the nth exterior power of your vector bundle, where E is rank n. That's kind of, hopefully that's fairly intuitive. And we're going to need oriented vector bundles substantially just to approach cohomology in a particular way. And what is that way? Well, I mean, it's a good, this is like analogous to de Rham theory, where you have, you're putting yourself in the setting where you're looking at manifolds. It's actually not much of a restriction, because any finite complex you can say embed in some Euclidean space that follows from basically the Whitney embedding theorem. That is one of the many results, by the way, that is worth learning if you haven't already. In fact, we'll use quite a few of those kinds of results. They're in most of them are in Milner's book, Topology from the Differentiable Viewpoint. much more comprehensive is Gilliman and Pollock's differential topology book. So anyways, you put your finite complex into a Euclidean space. You're using the fact that cell by cell, you've got manifolds, and you use some manifold topology to say the thing can be moved homotoped a bit to miss itself. And then you fatten it up. You take some open neighborhood which retracts on it. And again, there's some point set work to know that there is such a neighborhood. There's a neighborhood deformation retract onto the embedding of a finite complex. But then at that point, you've got a manifold. So in de Rham theory, you've got a manifold, and in that case, you've got a concrete way to manage cochains. So yeah, so in this case, what we're going to do is have a concrete way to represent cochains in a manifold that don't rely on differential forms, which are defined through calculus and thus mating characteristic 0. By the way, you don't need calculus. You can be more algebraic. That's what Sullivan did for a simplicial set. So you don't need that smooth structure in a different way. It's not really, as I said, you can provide it just for finite complexes anyway, or B for any simplicial set. Sullivan gave us a de Rham theory. So what's the kind of conceptual hook, so to speak, here? The way I like to think about it is that that chains are very concrete objects. So chains are concrete. They're small sometimes. Here's a chain in R2, maybe 5 this plus this. Of course, it's easy to draw what a cycle would be, and maybe 3 this plus 3 this plus 3 this or whatever. Whereas cochains, if you think about it, to specify an element of Thom from the chains into your ground group or ground field, ground ring, are transcendental. I would have to be able to tell you that I'm talking about singular chains at first, and morally, that's really what we want to do, is talk about something close to the singular chains. So I would have to tell you what the value of the cochain is on every element of the chain group. And again, de Rham theory addresses this in this lovely way. Using calculus, it says, I know a way to take a chain and produce a number. I'm going to use integration. So we'll only use the smooth chains, and that's also going to be true for the theory that I'm going to develop of Thom cochains. But then, for example, on R2 minus 0, if I look at d theta, that's just a perfectly good way to, if I've got a chain, and maybe it even sort of does something like this, I can tell you what d theta is, how it evaluates on that chain. Namely, it's going to measure the winding number, the total angle. Actually, it's not the winding number. It'll be just the total angle that I'm traveling around the origin. So if you think about it, that is the key geometry. So even in, say, finite simplicial complex, if I want to think about, maybe not R2 minus 0, maybe if I've got an annulus. I don't know if you've ever sort of looked closely at what a co-cycle is, but if I've got this triangulation, you can imagine what the triangulation of the annulus is going to look like. Then this is what a co-cycle looks like. A one co-cycle And again, I'm in the triangulated setting. So I have, you know, all sorts of um, other edges and things like that. It's triangulated. And what the significance of this cocycle is that if I go around the annulus, then at some point I'm going to have to cross one of these green edges. Really here, this is in the linear dual, so it's saying I'm going to evaluate to 1 whenever my path includes one of those. But if I have a full path where I began and end, this is at the same place, this is exactly going to count the number of times I wind around. And this kind of representative for the cochain really comes down to thinking about my path around the origin and saying, let's count the number of times I cross, say, this red line, because no other the green things that I drew at first, I meant to draw the other ones yellow. The green things that I drew at first were exactly what you need to include if you're going to travel around the annulus, or back around. So this is basically the idea of a Thom cochain. In this case, maybe let's still think about this as R2 minus 0. This is going to be our first example and our key example of a Thom cochain, array from the origin in R2, say the positive x-axis if you want to be concrete. Okay, so let's then make a what I'm going to call a pre-definition. And our pre-definition is just going to focus on submanifolds. So I'm going to have some submanifold of a manifold. Means it's proper. I don't care about, M doesn't have to be compact. Again, this R2 minus 0 with array is a great example to keep in mind. Its codimension, which is the dimension of M minus the dimension of W, let's fix to be N. Some other days it might be D, but today it's N. And let's predefine what we want to say is that tau W on some chain is going to be the number of times this map intersects W. Okay? So that's our pre-definition, not yet a definition. That's this idea to get going. So what do we need to do to make this a definition? There's actually a few things. First, a really key thing is that we want this to be a cochain, right? It's a functional on chain, but right now it's only makes sense to evaluate, really only predefined on sigma, which are smooth and which are transverse to W. Okay, and well, what we can do is define this smaller chain group to be the chains in M transverse to W, in which case this is now defined. It is perfectly good on the cochains transverse to W. In other words, the cochains where I'm only asking to be to give you a value on chains which are transverse to W. So so then a proposition will need, and certainly won't do today, our theorem, is that the chains transverse to W and M, things which are smooth and transverse, well, they sit inside all the singular chains and they give a full theory. So, so that's a key. In order to prove this, part of only going so far today is, let me make a note here. Could have made this warning to be honest. We want to use a lot in here, ideas of that were explained. They go before, but that were explained beautifully by Milner. As I said earlier, topology from the differentiable viewpoint. And actually this more comprehensive, there's some, Milner's book is one of my favorite potential undergrad texts or beginning grad texts. It just sort of covers so many wonderful ideas, but there's hardly any fat. There's very lean treatment. One perfectly developed idea after the other, a little bit more comprehensive, well, substantially more comprehensive, is Gilman and Pollock's differential topology. Perhaps I could look up some of the exactly where we use things, but it's the main transversality theorems are essential here. So to prove things like this quasi-isomorphism, we're going to basically, I mean, the thing is that the chains, I mean, chains is just this large, huge, uncountably generated abelian group, but it's based on a topological space, namely the space of maps from a simplex. And that topological space, one fact about it is, well, within the smooth chains, the ones which are transverse are open and dense. And that allows one to sort of homotop chains and just choose ways to take. So what you would want is to make a map back this way, a chain homotopy, and that can be done. So I don't know what level of detail will work with that, but that will be part of the story in any case. So that's one thing. So now, if what are we trying to avoid in case you haven't seen these ideas before? I'm supposed to be counting intersections. Well, what if I run along W for a while? So what if instead of crossing the x-axis, I stay on it? Or what if I kiss the x-axis? That looks like I'm intersecting it once, but in fact, as far as winding number goes, I really haven't contributed, so I shouldn't count that at all. And the point is, I shouldn't allow it to begin with. And then speaking of counting, these counts. So the next thing to go from a predefinition to a definition is these counts need to be taken with some care. Because, well, what's a good little example in our little R2 minus 0 example with the positive x-axis as my W. If I take some chain and do this, then it looks like I've intersected 1, 2, 3, 4 places, but some of them come with a plus sign, maybe this and this, as well as this, but maybe this comes with a minus sign. And so that's actually just winding around twice, which if you followed the curve, we'll look around over here. The intersection here makes it look much more like it's winding around twice, which it is. So what we need to do is, well, we can either take the this intersection count, which is really the number of preimages of W. So let me say that back here, let's be a little bit more rather than just think of them as intersection points. This will be a nice essential. In a moment, we're going to think of this as just the preimage of W under the map sigma. So where the count is happening is now happening in the simplex. And what that allows us to do is, well, we either count that mod 2, or let's assume, or we choose what's called a co-orientation of W in M. And what that means is an orientation on the normal bundle. Let's remember that this is just the tangent bundle of M restricted to W modulo the tangent bundle of W. So, so we're co-oriented, and then what Quillen and Pollock say is that normal bundles pull back, and then the fact that pullback behaves well with indo-functors would mean that exterior powers of normal bundles pull back, orientations pull back. I mean, you could do it more concretely than that, but things that we've been developing let us then know that sigma inverse of W is co-oriented. And in fact, by the kinds of main transversality theorems as explained in Quillen and Pollock, it's a co-oriented, well, it's codimension in submanifold of delta n. Now delta n is actually a manifold with corners, so that's a little bit more than is in Quillen and Pollock, but that's in this way, the manifold with corners is entirely elementary to deal with. So that means that it's, well, if it's codimension n of delta n, it's 0-dimensional. The normal bundle of a 0-dimensional manifold in something is just the trivial bundle, because the vector bundle over a discrete set is always trivial. And so we can then compare the co-orientation of this normal bundle with the standard orientation of, let's call it the tangent bundle. And that's just induced from the tangent bundle of the simplex. In other words, the simplex just has an orientation that we can rely on, and then we can compare the co-orientation we've pulled back with the orientation, and both are just orientations on the vector space living in the tangent bundle of delta n over that point, and we get our signs. And we count with pluses and minuses there. So here's a little exercise. Check how these conventions work for, say, M again is R2 minus 0, and W is the positive x-axis. In other words, I'm crossing the positive x-axis. What are going to be the positive crossings and what are going to be the negative crossings when I unravel these definitions? A word about, co-orientation. Orientation is a word that you hear all the time in topology, differential geometry, all sorts of other places. Co-orientation is much less popular, but it's the right thing here. So this is going to be perfectly fine to give us z-valued cochains even when M is not orientable. For example, M could be RP4 and W could be RP2. And there is an integer valued cohomology class. It is 2 torsion actually in H upper 2 of RP4. And this is gonna give us the right way to deal with that cohomology class, which if we wanted W which were orientable, I don't think we could represent that cohomology class. Okay. So, and then another thing we have to deal with, or else we run into some potential problems, is let's think about what kind of object is W. And there's going to be some flexibility here. The main property is some properness, which is baked into the definition of submanifold. So for example, a spiral going to the origin is not a submanifold of R2, even though, well, it's homeomorphic to R and it's sitting inside R2 smoothly, but it's not proper, so it's not a submanifold. But within there, again, we could restrict to submanifolds. And conceptually, we certainly want to think of that as a great case. And for a lot of applications, actually, it's lovely when you can find a cohomology representative by one of these Thom cochains of a submanifold. That's just a beautiful thing. But I don't think it's true in any generality that you really can take single submanifolds. A key thing, and especially as we develop this just a little bit more, is that we need it to be a submanifold with boundary. But maybe we restrict or we loosen things a bit. If we just have an immersion, that has a good normal bundle. I can again co-orient and go through. So that's easy level to generalize. Again, I'm not even sure what you get for theories. I'll talk about the sort of making these objects into a theory. Right now, I'm just making a single cochain. And you have to be careful because if I took all possible, here's what you don't want to do, take all possible W's, even as submanifolds, great. Then if I take 2 of them, the natural chain group on which I operate are things that are transverse to both. 3 of them transverse to all 3. If I take infinitely many, unless there's some local finiteness, so in particular if I take all, at the end of the day there would be no chains that are transverse to them all. So there's definitely some care in actually setting up a cochain complex with these. But again, for now, I'm just defining a single cochain in something which is pretty close to the original chain group. So we need immersions. If we bite the bullet and deal with manifolds with corners, then we can then we certainly can recover cohomology with such objects, and I'll say more about that a couple lectures on probably. But really, all you need is a proper map with something, and that goes to Quillen. So yeah, so sometimes I think of this as Thom cohomology, but really this the following generalization is all basically all due to Quillen. He has this lovely paper called Some Elementary Proofs of some facts in cobordism theory. I find that title hilarious. It's one of the least elementary papers. When I grow up, I want to read it. Somewhat of it, I can look at a lot of my work, and it's gone to. I think I should be able to soon have a much deeper understanding of it, because it uses a view of Steenrod operations, well, two views of Steenrod operations, one due to Landweber and Novikov that we'll talk about when we develop characteristic classes, and the other sort of equivariant ideas, and that's both my thesis and Thom Deek, and also recent work that I've been doing, sort of obsessed about symmetric groups. So anyways, Quillen has this approach to cobordism, which he then uses to give quote unquote elementary proofs. They don't involve Pontryagin and Thom and spectral sequences and that kind of thing. That's what he meant by elementary. But still, so what is this approach? Well, it really comes down to, if I have a proper map and I want to use this Thom cochain idea, I need to sort of pull back. I need some sort of co-orientation again. And so what we're going to do is, so for F, a map from W to M, we define an orientation of F. Well, let me actually be consistent with what we just said, a co-orientation of F to be an equivalence class of factorization. And the factorization is going to go from W to M through a vector bundle. So it's one reason I like to do Thom cochains in this setting. This is an application of these ideas. So this is a vector bundle. And this is an embedding, a smooth embedding. Okay. And we're going to say that they're going to be so E is a vector bundle, and I is going to have a choice of oriented normal bundle. Or what we can say is W has an oriented normal bundle in E. And then, so wow, so I took a map and now I've stuck any possible vector bundle in between, but I said equivalence class. And what do I mean by equivalence class? We mean that E is equivalent to E prime with those orientations. So once again, it's emitting just by abuse, choosing one piece of the data for the name of a co-orientation here. So E is equivalent to E prime if there is, say, some EW double prime, another vector bundle, which contains E and E prime, and then such that I is isotopic to the I prime, right? And here's a basic fact, and again, this follows, let me call it an exercise, that the space of embeddings of, let me just do the pi naught. Well, I'll do two things. This, if I embed W inside some, so first of all, if you look at that definition, suppose we're over a paracompact M, then we can think about a trivial bundle, right? And maybe M itself is embedded in something. So we really could, then W is embedded in a Euclidean space. So even though there's like knots, once you say include an S1 and R4, all of those are connected, and S1s and R5, et cetera, that's all connected. In fact, let me make it a two-part. In fact, this space of embeddings is contractible for high enough dimension. So these are good things to try to prove if you've never, well, even if you, as a good refresher, say, for Gilman and Pollock. Again, maybe some people want to, after this lecture, sort of pause, read a lot of Gilman and Pollock, come back to some of these ideas before going further. So what that implies is that a co-orientation is really just determined by that orientation of the normal bundle of W in E. So this exercise implies that there are exactly two equivalence classes represented by the two orientations on, the normal bundle to the image of W under I. Okay. Right. Okay. So we're getting now to our definition. Let's see. Oh, so an example of such for a co-orientation is, well, if we can take, so if F is already an embedding, then choose E to be M, the rank 0 vector bundle, and then we're good to go. And the definition agrees with what we had before. And the idea is now we make our definition. So what I'm going to do is I'm going to have my chain, and W is one of these co-oriented objects. I sometimes call these Thom objects. So I've got my vector bundle, I've got my inclusion. And again, so what is this? This is going to be, let's realize that this is, say, codimension N. So this will be codimension M plus N. okay, for those keeping track at home. And what we're going to do is we're going to pull some things back. So then over here, I've got the pullback of E. And that, by the way, is just delta n cross r m. Because we proved last time that pullbacks via homotopic maps are isomorphic, the identity map on delta n and a constant map are homotopic, and the constant map, you can quickly check, always pulls back the trivial bundle. So I've got this pullback bundle, which is trivial, and then I can also look at pulling back W, right? And then the point is that I can, if sigma is transverse to W, then upstairs, what we get is that the pullback of W and sorry, I mislabeled these. And I can think about this top pullback as really, I can think about the top pullback square as maybe a little bit easier because now W is embedded in E. But anyways, either way, if sigma is transverse to W in the sense of Gilman and Pollock, then the pullback of W is a zero manifold because it's going to be codimension n plus m in this space, which is dimension n plus m. And it's going to be co-oriented. So once again, we can define now tau W, so define on such a sigma to be the count with of this zero manifold. Again, for a lot of things, now, one thing to say is we will need this level of generality. For the applications we want these proper maps with these factorizations. That said, conceptually, it's probably best to skip that and really just think about W embedding into M, so that E is just M itself, if you will. So we're going to develop these ideas more, but I want you to have some time to sit with them, to play with them a little bit, get familiar before we develop the theory. Let's just, for now, let's give a couple exercises. Some are pretty, yeah, I like these. So for all of these, we're gonna have a map between manifolds, not necessarily of the same dimension. And suppose I've got one of these tau W, a Thom object on M and a Thom object on N. Again, we can think of them as submanifolds. And these are going to be, so let's first think about the normal variance. So define at the cochain level what should be the cochain pullback of tau sub V on N. So cochains should pull back. Let me prompt you to say by saying what conditions are needed on F. In particular, of course, F had better be smooth, you would guess. I'll go ahead and write that up here. But what other conditions, if any, do we need to define the pullback? And then a related problem for this one is then verify the homotopy axiom in the case that that I've got a cocycle. By the way, one of the main things we'll do next time is if W has no boundary, that includes again the positive real axis inside R2 minus 0, doesn't have a boundary, then it represents a cohomology class. So let me give you a hint if you haven't looked at it before. Look at the smooth proof of invariance of degree. This is one of those facts that little pet peeve of mine in our subject. Students tend to first prove invariance of degree using homology theory without sort of seeing it in its kind of what I would think of as its natural state in the smooth category, where degree is just counting numbers of preimages, and then homotopic maps pull back or have the same degree through something. Well, let me spoil some of the fun. You need the classification of one manifolds as a key fact. But let's also see if you can define some natural way to push a cochain forward. Again, we can repeat the question: what conditions are needed on F? Let me again spoil things a little bit and say more conditions are here are needed, because this is, well, it's funny, we call this F shriek, and it really says, oh, pay attention, there's something non-trivial going on here. And let me give you an exercise so that you can maybe know that you're on the right track. Show that your definition specializes to the transfer in cohomology for a finite sheeted covering map. So these are some ways to just start making sure you've got a sense for this definition. All right.